Questions on the reading? Material for today is Chapter 6 on stacks. Quick note, I'm going to try to not have stuff to go the entire 2 hours and 40 minutes, whatever the official time is, because I want to see the media briefing at 4 o'clock. Tuesday after class, my office was evacuated. It's just barely in the evacuation zone. So I'm just keeping an eye on the fire, making sure it's not going anywhere else it's not supposed to go. If any of you were affected,
I was told 2 weeks until my area was evacuated. I was all the way up in Monument. And I get the evacuation notice yesterday, pre-evacuation notice, right on the line between I-25 and between the two zones. Because on one side of the I-25, we have an evacuation center, not to say something. And on my side, just mountains and torch material everywhere.
Yeah. So hopefully the firefighters and the incident crew have that under control, and we won't have to worry about anything after today. Hopefully. So with that in mind, let's talk about stacks, which I don't think I can make any analogy between stacks and fires. Right. So I did get the iPad thing working finally. So the usual drawing for a stack is something that looks like that. Just kind of a bin that holds things. A stack is also referred to as a first in, last out structure. Basically, whatever you put in first gets buried by the stuff that you put on top of it, and you can only access whatever's on top. Stacks generally have three specific operations. One is a push operation, one is a pop operation, and the third is a peak operation. And we'll show each of those. So the pop operation, the push operation is when you put something in the stack. So let's say 5. It's really as complicated as it gets. Push, you put something on the stack. If you push again, so that's 5, push 4. 4 goes on the stack. Now, the diagram is useful because it shows that we can only access the top element. The only thing we can look at is that 4 on top. We don't know that there's 5. We don't know, right now anyway, how many elements are in the stack. We just know that there is an element on the top, and we can get to it. So if we go to a new page, and so we had 5 and 4, and if we pop, what we get at the end is 5. And usually the pop operation returns, always the pop operation returns the top item in the stack. Usually we save that somewhere unless we're just trying to get things off the stack and don't really care where they go. So the pop operation is really two smaller operations. The first operation being giving you whatever the top element on the stack is and removing the top element from the stack. So pop is the normal operation if you have, for example, a stack of pancakes, like I had for lunch today. You take a pancake off the top of the stack, you can't also have it still be at the top of the stack. That pancake is now on your plate. It's no longer on the stack. But with computer science, we can make copies of things very easily, and usually the default behavior of computers is to make a copy of things. So we have this peek operation. So if we have the same stack, 5 and 4, and we peek, the stack still has 5 and 4. And usually the only thing that peek does is show us what the top element on the stack is. So if we're not saving that somewhere, we're really not accomplishing. So in that sense, a pop consists of a peek and removing the top element. Questions on the things that we can do to stacks? On the usage side, stacks aren't really all that complicated. The question comes in, when would we use a stack? We use stacks an awful lot in real life. We might put our laundry into a stack, put pancakes into a stack. But in computer science, it's kind of difficult to describe this without describing other combinations of last in, first out, first in, last out, which both describe stacks, and other combinations of those. But there are very specific instances where the first thing we see is the last thing we want to worry about. One kind of contrived instance is if we were checking for palindromes. A way we can check to see if we have a palindrome is, in essence, to reverse a string, and we could pop it onto a stack. So if we have, let's see, dad is a palindrome. Does anybody not know what a palindrome is? A palindrome is a word that is the same backwards as forwards. So if we were to take the word dad and flip it around, it's still dad. Race car is another example. And it's not, punctuation doesn't matter, capitalization doesn't matter. So it's basically take the string, strip out all the punctuation and spaces, cram everything together, change it all to lowercase or uppercase, depending on what you want to do. Looks like I'm using uppercase here. And flip the string, and if the original string and the reverse string are identical, you have a palindrome. So things like madam on Adam is a palindrome. There are even some longer sentences that ridiculous length, but why you would ever use a palindrome in real life, I don't know. But there's a word for it. So if we were to test a word to see if it's a palindrome by using a stack to simply reverse the string, we could take each letter in turn, push it onto a stack, so we'd get that. And then if we, it's difficult to show since it's a palindrome, but this goes here, this goes next, and then this goes on top. Then when we pop things out, if we pop things out again in order, so my arrows are going to get kind of wonky. We can do that, and I'll draw another diagram demonstrating that this order actually does handle the reversal. But if we compare this and this, the letters are identical in the same order. So let's try something that's not a palindrome. Ear. So, obvious the order in which we push things onto the stack. But if we pop things off the stack in that same order, and I'll keep the arrows identically wonky, we get R, no, A, E. Not a palindrome. So when's an instance when this is actually useful? The book describes one instance as matching braces, parentheses, basically nesting. And the book does a pretty good job of describing that instance. So I won't repeat that. We have another instance that we'll be using. We'll be implementing a stack to handle this as part of the ongoing programming assignments for the semester. And that's in doing math. So we're used to seeing math written like that. This is commonly called infix notation. And of course we have order of operations. So this happens first, then we get this, then we get that. So this ends up being 20, this ends up being 23, and then this ends up being 17. And that's our answer. Turns out that it requires a lot of trickery and thought to build a parser to compute math this way on computers. Obviously, compilers do it because in Java you can write an expression like this and it computes it just fine. It gets the answer. But what it has to do is figure out what will happen first and do that, and then what will happen next and do that, and so on and so forth. And there have to be certain rules in place to figure out basically the whole order of operations. But there are ways of writing math like this so that there's absolutely no thought involved in figuring out what has to happen first and what happens next. And eventually we'll see that they use stacks. But the idea is that you start at the left and do the thing on the left. And as you go to the right, you do the next thing in order, and eventually you get the right answer. This is sometimes called postfix notation. It can also be called reverse Polish notation, RPN. And so, us being humans, knowing how order of operations work, we can look at this stuff and see what has to happen first. In order to, so in this expression, the first thing that we do is that multiplication. In order to be able to do that multiplication, we need the two numbers, and then we need to know the operation. So our starting point is the two numbers. So I should probably fix that so the iPad doesn't go to sleep. So there's our first number. There's our second number, and there are spaces. Can't really draw spaces here. Then we say multiply those two numbers. And basically that says take the two values to the left, multiply them together. So after we get to this multiplication, we get 20. Then we say we need a 3 and add that together. Then we need a 6. Then we need to subtract that. Some upsides of this is that we only have to store one intermediate value in memory. This particular expression is not real complicated, but if we had 5 times 4 plus 3 divided by 6 maybe, or maybe 6 divided by 3, that might make a little more sense. We'd have to compute an intermediate value, compute another intermediate value, and then subtract one or add those two intermediate values together. Which means we need to store 2 intermediate values somewhere in memory, which is not as efficient for computers. especially since as you get further on in the computer science program and start talking about computer architecture and organization, memory is slow, very, very slow. It's a lot faster than your hard disk, but memory is still pretty slow. Processors have smaller pieces of memory right next to the processor, but they don't have a whole lot of them. There's kind of a trade-off between the amount of space that you have and the accessing speed. So processors have access to a very small amount of memory, maybe 128 bytes or so, which really isn't a whole lot of space. If you're using 2 of them to store intermediate values, there are 2 fewer of these pieces of memory that the rest of your program can use. If you have an even more complicated expression and you need 6 of them, in most cases that pretty much exhausts the amount of processor memory that your program can actually use. So this notation has some benefits, and that's actually how Java bytecode doesn't really work this way. There are languages that do work exactly this way. All of the .NET languages, they compile down to something that does math exactly this way. And a computer that does math this way is called a stack machine. And the reason for that is, let's see if I can remember what I put there. 4 times 3 plus 6 minus. So if we use a stack machine, what that means is that the processor memory is a stack. All these values end up in a stack. So at the beginning of this expression, we start out with an empty stack. When we see the first number, we push that onto the stack. When we see the next number, we push that onto the stack. And then each of these operations is essentially a function that takes the top 2 elements on the stack, does something with them, and places the result back on the stack. So when we hit so this is 5, this is 4. When we hit the multiplication operator, it takes 5 and 4, multiplies them together, and puts the result back on the stack. So we end up with 20. When we get a 3, it pushes that onto the stack. Now, so 20 and 3, and we put 3 on the stack. So now, when we do the addition operation, it takes 20 and 3, adds them together, puts them back on the stack. And then 6, not very interesting. Now the minus does get interesting. Because of the way minus works, we can't just take the top 2 things off the stack and subtract one from the other arbitrarily. We do have to maintain order, and in fact, order is maintained for all of these operations, but multiplication and addition are commutative. So a plus b is equal to b plus a times b is equal to b times a. Not so with subtraction. So the way this is defined to work is that the top thing on the stack goes the way we would write subtraction, goes to the right of the minus sign. The next thing so this thing second from the top on the stack goes to the left of the minus sign. So in this case, we'd get 23 minus 6.
And that would give us 17.
So in the instruction language that we're writing an interpreter for over the course of learning our data structures, this instruction language does run on a stack machine. The way it does math is using stack-based math, and I think it's programming assignment 3 involves writing a stack. I think I have it called machine or something like that. And basically, that will handle all of the math. So the addition operation will pop something off the stack, save it in a temporary place, pop something else off the stack, save it in a temporary place, do the addition, and push that back onto the stack.
Questions? Okay.
So at this point, I think I've talked about everything we need to know how to use a stack and everything we need to know about stacks to use them for the programming.
What about implementing stacks?
I've already mentioned that most data structures are kind of an interface on top of some storage mechanism to abstract that storage mechanism away from the rest of our program.
The book's implementation of a stack uses a linked list,
and that makes it incredibly easy to manage the stack, because since everything is an object of a reference type,
we don't have to worry about how much space we're taking up, how long the stack is. We don't have to worry about if I'm storing more things in my stack or trying to store more things in my stack than I have space in an array, and then having to make the array larger or something. So what does that look like?
When we built a linked list, we kept track of the head and the tail.
When we're building a stack, we don't really care about the tail. We really only care about the head. So we can actually rename it something like top. And this is what the book does. In the beginning, top points to nothing, because we have an empty stack. If we want to add something to the stack, and we're using a linked list as the underlying storage mechanism, we can create a node that stores some data. So I'll use my example, and points to nothing. If we want to push something onto the stack, we don't have to do anything with the node that's already there. All we have to do is add something to what would be the head of our linked list, and make the pointer point to the right place. So all that we need to do is create a new node. I think that should have 4 in it. Make it point to the current top, and then change top to, instead of pointing to 5, point to this node. And the book accomplishes that with 1 line of code. And that was push. If we want to pop, so 4, 5, pointing to nothing, top points there. We can simply return the data part of top, so this part gets returned, and then make top point to its next. That's it. So when we implemented the linked list, we had a lot of code in there to make sure that we didn't lose references to things. That made sure that all of these references pointed to the things that they needed to point to. When we added something in the middle, the references got adjusted accordingly. When we put something on top, at the head, all the pointers got updated accordingly. When we inserted something at the tail, things got updated accordingly. All sorts of things going on. Because stack has a very specific and limited way of interacting with it, the pointer manipulation, or the reference manipulation, is almost trivial. So I don't remember how many lines of code the book used to implement its stack, but I would bet that we can probably implement an entire stack with using a linked list with the node class as a nested class in, let's say, less than 100 lines of code. Oh, right. So before we do that, peak is exactly the same as pop, except we don't adjust where top points to. So any questions on conceptually the implementation of the stack? So let's call this, I think the book calls it linked stack. So since we're going to use a linked list, first thing we know we're going to need is some sort of node. So let's get that out of the way right up front. And as a nested class, call it node. And the book makes this use generics, so I'm going to make this use generics as well. We'll use our placeholder type. We'll call our placeholder type E. So a node that stores type E should have something of type E called data, and something like that called next. Let's also make a constructor that takes 2 arguments to make it a little bit easier to deal with this node. And we'll simply set this data to data, and this next to next. I could also make a Star Trek reference and say I'm glad somebody got that.
Do we really care about a constructor for this linked stack? The only reason we used a constructor for the linked list was to give it an initial capacity. I'm not really concerned about giving this an initial capacity because we're using linked lists. It's dynamically expanding. It contains as many nodes as we have things stored in it. So I don't think we really have to worry about that. But we know that we have to implement 3 operations. We need to implement let's start at the beginning, a push, which should take an E we'll go back and fix the signatures once we have all of them set up. A pop, and a peak. Now, push, we're taking data and we're putting it into the stack. So this doesn't return anything. A pop, we're taking something off of the stack and giving it back to the calling class. So this does return something. And if we have a linked stack of type E, it should return an E. And all of these should have, no they shouldn't. And a peak, same thing. All right, so let's replace all these, or stub all these methods out so that, assuming we haven't broken anything else, it should compile and make sure that we don't need to return anything there because it's void. And I guess we'll need to save this. Linked stack, yes, save. And let's see where it breaks. Okay, cool, it didn't break anywhere. I like when that happens. Okay, so I mentioned for push, all we have to do is kind of move the top node down and put a new top that points to the old top. So I guess we might need something like that so that we can do something. So one way to do this would be, we know we're going to move the old top out of, or the what is at this point the current top out of the way, so we can do that. That kind of moves it down. Now we need to create a new node that stores data and points to old top. But we probably want to hold on to that node, so, and we want top to point to it. So that has all the functionality it needs. The problem is that, well, not necessarily the problem, but it's not as elegant as it could be. We don't actually need to store top in another variable just to use it again and then forget about it. So we can actually just get rid of line 15 altogether and change this.
Questions? So we're storing in top a new node that stores the data we're given and points to top, or what top was. So it looks like we're well on our way to having far fewer than 100 lines of code. Pop. Let's first assume that we have something there to pop. So obviously we shouldn't return null. Let's get rid of that. The first thing we want to do, ideally we would return the data that is contained by the top node and then move top down. We can't do that because we can't run code after we already return. So one way to do that is to store the top node somewhere else temporarily, move top down, and then or return the data that we need to return. The other option is to store the data temporarily, which I think is probably a better option. So eTemp equals top.data. And then we'll make top point to the next node. And so at this point, what was pointed to by top, the old top node, is no longer pointed to by anything else. It's a reference. It's an object with no references to it, so it'll get garbage collected. It'll just go away by itself. And now we can return temp. Any questions on that? So, with that in mind, I've mentioned that peek and pop are very similar, and looked at one way, pop does peek and some more stuff, and looked at from a different way, bless you, pop is kind of a special case of peek. So Lynn, would you like to tell me the only statement that I actually have to write here in order for peek to work? So, I'll give you a hint. It starts like that. Yes. Right, so that should be our entire implementation. Now, to make it a little bit easier to deal with, I happen to like the toString method. I think it makes debugging vastly simpler. Most things, no, I can't say that. There are a lot of things in Java that don't have a toString method, and it gets kind of irritating. But in general, a toString method is a good thing to use. And I know there were some questions on how the toString method worked on the PA1. Basically, it works because of something that we haven't talked about called inheritance. And it really, the object class in Java, the thing that every other class in Java automatically gets its members from. So everything in Java is an object by default. it has a two-string method. It has a default two-string method. And that's how when you do system.out.println, something that's not a string, Java takes that as an object, calls the two-string method that's defined in object, and prints something out. Which, the way object is, that two-string method is defined, it says print out or return as a string, actually, the name of the class that this object is an instance of, followed by, an @ sign? And then followed by the reference, some reference indicator, which is usually not very helpful. It tells us what kind of thing the object is and where it is, but it doesn't really tell us anything about it. So in order to be a little more helpful, we can write our own two-string method. The only way this works is if the signature of our two-string method is identical to the signature of the two-string method that is already defined by the object class. And that signature looks something like this. Oh, that's the end of signature. Okay. The important parts. Important part number 1. It returns a string. Doesn't return anything else. It only returns a string. Important part number 2. The method name is toString, lowercase t, lowercase o, capital S, lowercase everything else. Third important thing, it does not take any arguments. Fourth important thing, which is not required in order to work as intended, but is kind of a convention in good programming, it does not print anything out. Anything that should be passed anywhere else should be returned as part of the string that is returned. So it is technically incorrect to have a system.out.println statement inside a two-string method. So let's start out with a string, an empty string. And I want to basically iterate through all the elements and add them to the string, followed by a space. No, actually I'll follow it by a new line in case it's some object that has some strange value that takes up a lot of space on one line. So what we'll do, we basically need some way of iterating through these things. And it basically follows the same method as the linked list did. So we start out with a node that contains an E, and we'll call that temp. And we'll start it at pointing to top. I'll get back to the while condition, but we know that while we iterate through these elements, we basically want to print out the data portion of the node, or sorry, add to the string that we're going to return the data portion of the node. However, the data portion of the node may or may not be a string. So while it might work, Java might let us do something like that. It's not really describing exactly what this does. So, since I mentioned that every object has a toString method, automatically, whether it implements it or not, we know that we can call toString on the data object. And since everything follows this signature, the toString method will follow this signature. We know that it will return a string. We can add two strings together, so we know that string plus equals another string is going to work. And how do we want to get to the next one? We already have a next pointer, so we can do something like temp equals temp.next, exactly like we did when we were iterating through the linked list. Now this while condition, it should be exactly like when we were dealing with linked lists. Anyone want to take a stab at what that'll be? I'm sorry? Almost. So let's to kind of work off of that. Let's say that we have a completely empty linked list. Completely empty stack. If we call this toString method, line 29 will create an empty string. Great. Line 30 will set temp equal to top. If it's a completely empty linked list, top is going to be null, which means that temp is going to end up being null. So in line 31, if we try to test while temp.next does not equal null, we'll end up with a null pointer exception because temp being null has no next. So with that in mind, how would you change that condition to work in that situation? Combine the two. So it turns out that you just have to have while temp does not equal null. And that will work. You can do kind of inductive reasoning if you really wanted to, and say that if I have a stack with 4 elements in it, when I get to that 4th element and I test temp does not equal null, that'll be false and it'll jump out of the while. But we won't end up with any fence posting errors or off by 1 or anything like that. So we have our initialization, our condition, and our approach. So now we have to actually return something. And in theory, by this point, we have something in str. So we can just return str. I'm actually going to specifically initialize that to the empty string, because if I don't initialize that to the empty string and I try to print out an empty list, an empty stack, it will return, that toString method would return null, which means that system.out.println would return, or it would print out null in parentheses, and then that would also be what it would print out if I tried to print out an object reference that itself was null, which is kind of ambiguous. So in this case, if there's nothing in the stack, it will return str. I also said I wanted to put a new line between them, so I should probably do that. And we're pretty much all done, and 38 lines of code. So I think we did pretty well. The book, let's see. think the book implemented a couple other methods. They implemented a clone method. If you've been following along in the book, one of the earlier chapters talks about clone and why it's important when you have something that contains references to other objects. Because if you simply copy the class and copy all the references, now you have two data structures, two instances of data structures that all point to the same data, and that's bad. Excellent talk, Google Tech Talk that I've seen. It talks specifically about global state and why it's bad. But a lot of the concepts that the guy talks about apply in improperly cloning data structures as well. When you have two data structures that both point to the same data, and you change data in one, not expecting the other data structure to change, and it does, that's bad. So maybe toward the end of class I can search for that, and it's like an hour long, so we won't watch it in class, but I do recommend watching at least the first half hour of it before you start taking questions. So they implement an isEmpty method. We've already talked about what it means for a stack to be empty, so I won't go through that. But their implementation is pretty tiny. Contrast that with the implementation of stacks using arrays on pages 338 to 340, which is 3 pages. The linked list implementation of the stack is a page and a half. So both implementations have their upsides, both implementations have their downsides. Certainly this implementation is a lot shorter, a lot easier to code, a lot easier to think about. But it does involve, you have to make sure that all your references are consistent. So let's make sure that compiles and create some sort of test class. And so someone pick an object to store in this linked list. Let's see, we've done ints. We did integers with this stack. Let's do. We could do booleans. That would be kind of boring. Let's do characters. So we want a linked stack. Does anyone remember offhand the wrapper type for the character? The character primitive type. I'll take that as a no. I think I remember what it is. There we go. I remembered incorrectly. Good thing I looked it up. Okay, character. Character. There we go. we'll call it stack. The very descriptive name, stack. New linked stack character, and no args constructor. So now we have a stack. Let's go ahead and print it out. And let's start with just that. I promise you, this will not be very interesting, this particular run. A single line break. No, not even. That's just because of the way Dr. Java does things. No, that's because I have the println in here. So let's add things to the stack. Stack.push. Let's go the long way about doing this. And let's see. Let's now pop and we will print that out. And we'll also print out stack. Then let's peek. And I think at that point, you'll get the idea. Let's see. So this is from line 4, printing out an empty stack. Then we print out these lines, these 6 lines, are printing out the stack after we push all the letters in hello, and we can see O is on top, and then the capital H is all the way at the bottom. And this is kind of confusing because we print out temp first, which is O, and then the stack, which is the rest of the letters in hello. And so O is very clearly not at the top of the stack anymore. It's been thrown away, returned to us. It only has 4 things. And if we peek, we get L, and then the stack is unchanged. Any questions on that? So let's add that isEmpty method real quick. isEmpty. And this will return top is equal to null. If top is equal to null, it's empty. If top is not equal to null, it's not empty, so it should return false. And let's go back to linked stack main and implement a program that checks for palindromes. So we'll do this as a it'll ask for input. We'll type in something, and then it'll tell us whether or not it's a palindrome. So import java.util.scanner. We'll still use the stack. Get rid of all this. And let's say scanner keyboard equals new scanner. By the way, there are easier ways to do this. There are methods that exist to reverse strings. So we really don't need a stack to do this particular thing, but it's a good example of how to use a stack. So before I put it onto the stack, before I push everything onto the stack, what do I need to do to this string? Well, I need to bring it all to one case, because palindromes are case insensitive. So let's say test string equals test string dot to lowercase. Other things that I need to do. I need to get rid of spaces. Turns out that there's a method that does that kind of thing. Let me make sure I have the method signature right. Before I started teaching Java classes, whenever I needed to go to the API documentation, I would pull up Google and type in Java API documentation, hit enter, and click the first result. Now that I teach these classes and I have a link to the documentation on my websites, I've started going to the course website just to find the documentation. So, very useful. What am I looking for? Yeah. There we go. String. Take it. need to be in the R's. So we have replace a single character, replace all regular expressions. Don't need regular expressions. I think there's actually other methods that might be helpful. Nope. Let's see what a char sequence is. All known implementing classes. String. Okay, so it's a string. So let's change replace. We could go through and replace all punctuation, but I will just say I don't want any punctuation here. Without punctuation. Okay. So at this point, now I have a clean string. There's also a method on string that will be very convenient, which is this one right here, 2-character array. Basically does exactly what the method says, which is gives me back a character array. So what I'm going to do is for character, there we go, C in, what did I call it, test string dot 2-character array. Stack.push C. Any questions on what I'm doing so far? So now, it would have been really convenient if I made the toString method of linked stack print out everything all or return a string with each of its elements, 2 string values, all on the same line, no white space in between. Because then we basically get the entire stack kind of turned on its side. Flopped down to the left. But we don't have that. So what we have to do is we'll reuse test string. So test string equals empty string. Note about programming, reusing variables for 2 completely different things is generally a bad idea. Because then later on in your code you might try to use it for the first purpose and it has some completely different value in it that means something completely different. And those bugs are incredibly difficult to track down. But I'm not going to go back and change this program at all, so I'll reuse the variables. So while stack is not empty, test string plus equals stack.pop. Set string. Test string.
Questions on that? Does everything I'm doing make sense so far?
So now, now's when I realized that I want to use the original value of test string, so reusing that variable name was not a good idea. So we will call this reversed string. And now we'll do something like if reversed string equals test string, then it's a palindrome. Otherwise, not a palindrome. And that's almost as long as our linked list or our stack implementation. All right. Questions on the implementation of our palindrome test program? Somebody wasn't watching. There we go. That makes more sense. Yeah. Cool. I'm really not making it all that hard since I didn't capitalize anything. But hooray, that's a palindrome. Was when ear is not a palindrome. Dad is a palindrome.
Anything else that you want me to show pertaining to stacks and their use? So with that in the yes, yeah. So
Let's say, so after we put stuff in the stack, let's call, stack. So that will end up calling the stack's toString method, which means that it will print stuff out. If I did not implement a toString method here, that's what I'd get.
Linked stack at 420A6D35, which is absolutely useful. I have no idea what's in this linked stack. It doesn't tell me anything about it.
So the purpose of the toString is really, it's mainly debugging, the way I use it anyway. Sometimes it makes sense that you're actually going to print out an object. But Java by itself doesn't know what it means to print out an object. So if you're ever going to print out an object, toString makes it easy. And it's also separation of responsibilities. It means that if you want to print out a specific object, you don't have to know anything about that object. Nothing. You need to know absolutely nothing. Because everything in Java automatically has a toString method. You know that you can do system.out.println some object, and you'll get something out. It won't crash. If that class has a toString method implemented, it'll hopefully print out something reasonable and might be useful. So if you get into later on, wrong class. So later on in the other class, they'll be implementing a sort of a fleet management sort of thing, and I'll have them implement a toString method on each object. Being a fleet management thing, it'll be basically a very rough collection of cars. So basically an array of cars. And I don't want them to have to figure out, is this particular car a Mustang or is it a Ford Crown Victoria? I just want them to say, here's a car, print yourself out, do something intelligent. And if it's a Mustang, it'll print out, I'm a Mustang. If it's a Ford Crown Victoria, it'll print out, I'm a old-looking kind of police car thing. So the program that they're writing, the main program, doesn't need to know anything about the implementation details of the individual data structure. Well, in our class, data structure, in their case, car. So in a case like this, especially, the book gives two implementations of a stack. One stack uses a linked list. One stack uses an array. When we're using a stack, we don't want to have to worry about what the underlying memory management model is. That's the whole point of the data structure, to abstract that away from us. But if we don't have a toString method and we want to see everything that's in that data structure, we need to know about the internal details of how the data structure manages itself. That's bad. So if both the array stack and the linked list stack implement a toString method, no matter which one we're using, we can call toString method. We can assume it has a toString method and just print it out, and it will print out something sensible. Does that answer your question? Okay. So, in a very short minute, I want to talk about, now we've talked about two different data structures. Well, kind of two and a half, if you consider the array data structure. Array is basically the only sort of data structure that Java provides. It's a starting point. But in this class, we've talked about two data structures in particular, the linked list and now the stack. And they're very different. Linked list, even though in this case we use the linked list to implement a stack. And that'll be something that we'll see as we go through data structures. It's not uncommon that one data structure can be the underlying data store for another data structure. So a linked list has a head and a tail and is very, more or less one directional. You start at the head and go to the tail as you traverse it. But it also has random access. You can get access to a specific element somewhere along the chain. You can insert an element somewhere along the chain. But a stack has a very specific, very restricted set of operations that you can do to it. And this kind of forces you into using it as it's designed. So it's good for specific applications like the math application we looked at, and the parenthesis and curly brace matching that the book talks about. Stacks aren't good for just general data storage. Storing a collection of items. Linked lists are better at that because they're more general. They allow more freedom. So stacks are oriented toward very specific applications. So any other questions on anything we've talked about this semester? Okay. We have a homework assignment due tonight. We have another homework assignment out today, due a week from today. You guys can take a 10-minute break, come back, or not come back. You're welcome to work on either homework assignment. I'll be here for a few more minutes to answer questions, but I do want to leave a little bit early so I can be in front of my computer in a quiet place so I can watch the press briefing.